Okay, now I'm going to introduce Emma Brunskill, who is our first keynote speaker of the conference. Emma is an associate professor in the computer science department at Stanford, where she and her lab aim to create AI systems that learn from a few samples to robustly make good decisions. Her work spans algorithmic and theoretical advances to experiments inspired and motivated by the positive impact AI might have in applications where experimenting is costly or risky, such as education and healthcare. Emma's lab is part of the Stanford AI Lab, the Stanford Statistical ML Group, and AI Safety at Stanford. Before joining Stanford, Emma was an assistant professor at Carnegie Mellon. She holds a bachelor from the University of Washington, master's from Oxford University, and a PhD from MIT. Her work has been honored by the NSF Career Award, the Office of Naval Research Young Investigator Award, a Microsoft Faculty Fellow Award, an Alumni Impact Award from the University of Washington, as well as multiple Best Paper Awards, both for AI and machine learning work and for work in AI for education. She served as the co-program chair for the International Conference on Machine Learning in 2023. Today, she's talking to us about efficiently learning personalized policies.
Thanks for the lovely introduction, and it's really a pleasure to get to be here today. I think this is an incredibly exciting combination of fields. And I'm going to be talking to you today about some work that I've had the pleasure of doing with a number of different collaborators. And I'm going to start by an example that continues to motivate me. So raise your hand if you've ever seen The Matrix. Okay, a lot of people have. If you haven't, I recommend it. It's sort of a classic in sci-fi at this point. I think one of the things that when I think about what AI might enable, I love to think about this scene in The Matrix where Trinity, who is one of the main characters, needs to learn how to fly a helicopter. And for any of you who've ever learned to ride a bike or drive a car, this is normally a painstaking process that takes weeks or even months. But in the movie, there's this wonderful scene in which she just downloads a program into her head, and in 30 seconds, she can fly a helicopter and help save the world. And I think the reason I love this example so much is because I think it really illustrates the idea of AI and computer science to really augment the goals and the intentions and the dreams of individuals. And instead of thinking of AI as potentially being a replacement for humans, which is a conversation that's increasingly important to be having right now, given the success of large language models, I think we can think about sort of how we can think of augmented intelligence, and in particular in these things around learning and skill acquisition. So in particular, in my own work, I really think a lot about sequential decision-making, things like reinforcement learning and multi-arm bandits, and thinking about how we can accelerate the pace at which we learn to do things like skill acquisition or education or other areas. And I think one of the challenges is that in many of these fields, we don't have good solutions yet, or the solutions we have are not sufficiently adequate. So I was at a conference on reinforcement learning a couple days ago, and we were hearing about some incredible results from DeepMind, in which they now have an AI that can perform at the silver level for the Math Olympiad. But the population of individuals that I work with are often 8th grade students, and there about 1 in 4 students can't actually do even basic sort of equations with integers. And so I think we really need to accelerate the progress at which we find effective solutions for these sort of applications. So in particular, when I think about this, I think of there sort of being 3 main buckets of type of work that we do in my lab, which is thinking about how do we acquire strategically better data, how do we leverage that data better, and then in general, are there ways for us to acquire or synthesize more data? And I'm going to talk to you today very briefly about some of the things that we're doing in 2 of those categories. So the first thing that I want to highlight is that I think this notion of the need to do strategic data collection comes up in an enormous number of areas. So of course, there's sort of things from statistics and experimental design that have been known for a long time, but this also comes up in artificial intelligence a lot when we think about creating agents, whether robots or online systems for commerce, that can strategically gather data. And the reason I put up this particular graph is this is just a simple graph that illustrates the difference between polynomial and exponential growth in terms of how much data is needed to solve particular problems. And so it's an area that really comes up in many different situations. And I think in particular today, I want to talk about sort of what data do we need and how do we acquire that data when what we want to do is learn personalized policies. So in particular here, I'm interested in the case, which I think is increasingly feasible, where what we can do is we can actually learn a different decision for every single individual. And in this setting, one of the challenges is that there's really an enormous number of personalized policies. So if we move from thinking about sort of standard randomized control trial design, even with stratification, in these settings, we now can think about the space of different contexts or the space of features that we're considering, as well as the space of interventions or decisions or actions. And that, of course, is an enormous combinatorial space. And so one of the challenges that we wanted to think about in this case is how do we do experimental design for learning personalized, contextualized bandit problems? So in particular, we wanted to start with one of the simplest settings we could think about, which was stochastic linear contextual bandits. Stochastic linear contextual bandits are the setting where we get to make a decision for a particular context and observe a reward or an outcome. And it's a very simple model because what we're going to assume is that there's a distribution of different contexts, such as different customers, for example, and then we might have actions, which could be, for example, different articles we could recommend to them to read. We're going to assume that we have a feature extractor that can take in, say, information about customers and information, say, different features that describe an article, and use that to create a particular feature extraction phi, and that the rewards and the outcomes themselves are actually linear in that. So the thing that we don't know in this case is theta star. We don't know the parameter that determines the outcomes given this input. So in the setting, what we wanted to consider is a very simple question, which is how do we do static exploration in order to minimize simple regret? So in particular, what we're going to assume is that we have sort of a data collection decision policy. And when we run this, we can gather data. We can get a series of states and actions and observe the outcomes. And then what we want to do is use that data to fit an estimate of our unknown parameter theta. And then once we have that, we can extract a greedy decision policy. So we can act greedily with respect to the parametric model we've just learned. And then we want to evaluate the suboptimality of the resulting decision policy. So the idea in this case is that we have sort of a fixed experimental period. We want to best use that experimental period and characterize how big that needs to be so that eventually we can learn a policy that is epsilon optimal. Now, I just want to highlight here that in particular, we're going to be thinking about optimality here averaged over our context space. And this is a little bit different than often the pack learning setting that we often think about in computer science. So we're only being judged on our average expected regret over the full context distribution. So I just want to highlight here that there's a couple things that we want to note. We're assuming that we're in a setting where we cannot change our exploration policy while we gather data. So one of the things that motivated this setting was some of the work that we've been privileged to do with War Child, which is an organization that supports children in conflict regions. And they often provide educational interventions, including tablets, to kids, but they often do not have reliable internet. They deploy these tablets with educational software on them, and they can, update them about every month. So in these settings, they were interested in thinking about things like, could we run an experiment to improve our educational software? And this was very different than the sort of online adaptive setting that we might have in sort of online commerce. So we're going to assume that we have access to this sort of static exploration policy. And we're also going to assume that we have access to a large amount of historical context. And you could think of this as, for example, all the data you might have about customers historically. And you might not have any information about whether or not they like some new articles you might want to show them, but you do know something about their sort of features. And we're also going to assume that we have access to a known state action representation. Now, I just want to highlight that there's been an incredible amount of research on the contextual bandit and multi-arm bandit setting. The majority of that work is focused on cumulative regret, which is the idea of saying, how do we evaluate the performance of that algorithm at every single time step compared to the best thing we could have been doing? There is also quite a bit of work on best arm identification where you don't have context. And then there was just starting to be some limited work on the setting we considered, but it really had some very prohibitive bounds in terms of the amount of data that was required. So I just want to explain sort of the intuition of the approach that we took. One thing that you can think of defining is sort of what is the online covariance matrix over the state and action space as one takes action, makes decisions. And it is known from linear bandit analysis that you can bound the regret of our algorithms according to the expected distribution of the worst norm of a particular state action feature with respect to this covariance matrix. And so in particular, this has been done already for cumulative regret analysis. What our observation is that if we want to do well, what we need to do is get states and actions that cover the space. So if we can sufficiently cover the space, we're going to be able to learn a good parameter vector. If we can learn a good parameter vector, we can extract a good greedy decision policy. But the critical thing to notice here is this has nothing to do with the actual rewards that you observe. This is just about whether you cover the state and action space, and you can evaluate that independently of actually gathering the data and observing the outcomes. So in particular, what we observed is that given that we know what the state distribution is, and given that we can predict what the state action feature representation would look like, we can plan in advance to know what our covariance matrix would be likely to be. So we can plan how to explore without assuming anything about what the rewards are. And then we can use that policy and actually use it to gather data and observe real rewards and feedback. So this is a case which we're often seeing this generally in computer science right now, particularly machine learning, where what we're doing is we're leveraging unsupervised data. And here we're using this in a way to define what that covariance matrix might look like. So part of our interest in this work is to understand how much data we might need. So for example, could I go to Warchild and say, this is how much data we're going to need to collect so that we're going to be able to learn a near optimal policy? So it's similar to sort of sample size calculations we often do in statistics, but thinking about it so we can find a near optimal simple regret. And the key thing that I want to observe here is that the amount of data we get in general will scale with the dimensionality of the feature representations that we're using, as well as inversely with how accurately you want to learn something. So do you want to have a small simple regret at the end? But the thing that I want to highlight in this case that we found a little bit surprising is that it turns out from a worst case perspective, you don't actually lose anything by this static setting. So by assuming you have to pre-specify what your decision policy is for gathering data, you don't actually lose anything compared to being fully adaptive. So that was quite surprising to us. Now I just want to give sort of a quick illustration of how well this might work in practice, because of course the goal in this case is to actually use this for real practical problems. There's a data set from Yahoo from a while ago now where it looks at people being given recommendations and whether or not they actually clicked on those articles. And this is a pretty high dimensional data set. So it's about 700 dimensions, and we projected it down to 300. And the idea in this case is there was sort of some previous curation process, so each individual would have 20 potential actions that they could receive. And we want to look at which ones we should ask about so we can learn a good policy for the future. Now, I just want to highlight that we looked at this particular data set because we thought it was almost definitely misspecified. We thought that the reward model was probably not linear in this space, and we wanted to understand if our algorithm could still be helpful in this natural setting. So what you can see here is that on the x-axis, this is the amount of data that we get in sort of our offline exploration period. And on the y-axis, it shows the performance of the policy that we could learn with that data. And then if we were to deploy that, as evaluated on some held out data. We consider different forms of regularization in this case in terms of the linear model, but the critical thing that I want to highlight here is that in comparison to gathering data randomly, then we can get a significant benefit by using our more strategic data collection strategy. And that's true even though the system is misspecified. So this was sort of our early foray into thinking about how can we strategically design data so that after we have a fixed experimental period, we'll learn a good decision policy. We've done a lot of follow-up work on this, and there's been a number of other papers, including by some people here at Cornell, who've been thinking about this setting. But I think that this is sort of just one instance of the fact that it really can have an enormous improvement to think strategically about how we gather data when we want to learn personalized policies. So the next thing that I want to talk about is thinking about a decision-pretrained transformer. So one of the things that was slightly unsatisfying in the work that I just mentioned, and really is a common challenge in a lot of reinforcement learning and contextual bandit work, is that the algorithms that we have make particular parametric assumptions. So the assumption I made before was that the system really was a linear model, and our theory relied on that. It turned out that our empirical results were somewhat robust to that, but it's a very common assumption. And I think in reality, for any real-world complex system, we don't know what the model class is in advance. And of course, that's a typical thing in machine learning, but one of the big challenges, I think, when we go into these settings is that we are actively gathering data under the assumption that things might take a particular parametric form. And so I think that has the potential to go much more radically wrong than for just simply fitting a function to some fixed data. So we wanted to think a bit about this, and we'd started to, together with some wonderful colleagues, including Susan Athey, we'd started to think about sort of loosening what we were trying loosening these type of assumptions so we could find kind of best in class for policy classes. But we felt like this was really open, and it was really, kind of illustrated by this kind of toy diagram, which is that in general, as we gather data, we have a choice to make about sort of what models we're using and parametric assumptions we're making. And if we use something that is overly expressive, like we use like a 200-layer neural network to solve a very simple linear bandit problem, it will be able to express that, but it means that we'll get a huge loss in terms of performance with limited amounts of data. On the other hand, if we pick something that is too simple for the decision problem that we're looking at, then we're going to get significant bias in that model approximation, and so we'll get significant performance loss. And the challenge, of course, is to figure out, what is the correct model class when we don't know this in advance, and can we realize that even though that's unknown. And so in particular, as a way to tackle this, we wanted to think about a setting with multitask learning. So we've done some different lines of work, and there's been some other lovely work by other people as well, thinking about online model selection. But a lot of it sort of has to rely on regret bounds for the algorithms that, again, only exist for certain classes. And so we wanted to think a little bit differently about this over the last couple of years. And in particular, we wanted to think about the case that increasingly we have many systems that are solving a whole sequence of tasks. And could we leverage that somehow to kind of identify what the model class is, or sort of get some good generalization performance? So the setting that we're going to think about here is where we have an agent that is doing a series of tasks. So in a particular task, it might have multiple episodes. So you can think of this like, a reinforcement learning agent that's learning to play a series of Atari games, Atari video games. It could be a series of recommendation agents, et cetera. And we're not going to assume that we have particularly good data in each of these episodes. We're not going to assume that this is sort of an optimal expert performance. It could be from random, it could be from a bandit algorithm, a reinforcement learning algorithm. We're pretty agnostic. But what we are going to assume is that by the time we finally finish each task, we could learn an optimal policy. So we have enough sort of data that we gather in each task that eventually we can learn an optimal policy, which again may not have ever been realized in the original data or used to collect in the original data. And so in this case, what we want to use now is to think about whether we can use transformer models, which have completely taken over machine learning and AI. They're the backbone behind ChatGPT and other systems, and see whether or not we might be able to leverage them in this setting. So in particular, as many of you know, transformer models were originally proposed for supervised learning tasks, in which we actually know what, say, the optimal output is, in comparison to reinforcement learning and bandit tasks, where we just get this sort of censored data over a reward for the actions that are taken. Now, there'd been some recent work called Decision-Transformer, which tries to apply transformers and these really powerful architectures to offline data and use it to learn good policies. But it was really unclear whether or not we could kind of leverage this really complicated, powerful function approximator for the task of sort of speeding up online exploration in the case where we don't know the model class. And again, just to be clear here, our motivation was transformers are incredibly powerful. They can, represent a huge number of function classes. Could we use them to do something like model selection automatically? So there had been a little bit of prior work starting to think about things related to this. There's this notion of algorithm distillation. And the idea in this case was to say, if we have these series of tasks, where maybe a reinforcement learning or multi-arm bandit algorithm is being used to gather data in each of them, could the transformer essentially learn to mimic that algorithm? And so that's why it's called algorithm distillation, because the idea is that you could just learn the algorithm from directly observing the data. And they had some really nice promising works last year at ICLR. But one of the challenges of this is that it's only as good as the algorithm that was used. So this is essentially just learning to mimic the algorithm that's inside of your actual data. And that means that you need really good data or really good algorithms to have been run in order to get sort of good performance. So what we proposed instead is something that could be a lot more flexible, making this assumption that eventually we do know the optimal performance for each task, but we don't actually have to gather data using that optimal policy. And we call this the decision-pretrained transformer. So the idea in this case is that as you are learning with the transformer, you're going to keep in your context all of the decisions that you've made so far. And then we're going to be using that to, given a new state, try to predict a distribution over what the optimal action is for this particular state. Okay. And we're going to train this decision pre-trained transformer using our historical data, where the key thing is we're still going to treat it as a supervised learning task and train in that way, but we're going to leverage the fact that we knew what the optimal action is for each state at the end of the task and go back and relabel what we should have done at every single state. So essentially, we transform our existing data into a new data set, which instead of having the actions that were taken by the algorithm or randomly or however your pre-training data was generated, we go back and label it with what was the action it should have taken at that case. Okay, so that's the process that we do. And that means that when we want to solve a new contextual bandit task or reinforcement learning task, we can put in sort of our new state, and it will predict an action. And then we can kind of build up and put the episodes as we work in this new task inside of our in-context data set. So I think, to me, the really interesting thing about this is how this is essentially isomorphic to Thompson sampling. So Thompson sampling, as many of you know, I know a number of you in the audience have worked on this area, but as a quick primer, Thompson sampling and posterior sampling is a Bayesian approach for learning to make optimal decisions, or can be used for learning to make optimal decisions in bandit and reinforcement learning problems. And essentially, it can provide a way for us to explicitly have a distribution over what is the optimal action in every state. It is a beautiful framework. There are known Bayesian regret bounds for using this type of approach. However, one of the big challenges is that sort of as part of the subroutine, it requires you to do Bayesian inference and to compute these posteriors. And this is often very computationally intensive to do in a way that accurately represents the posterior. And so for a long time, a lot of the work to do this really relied on relied on sort of very simple parametric classes where we'd have conjugate priors, or could be very computationally intensive. But what we can actually prove in this case is that under some assumptions, what our decision pre-trained transformer is doing is it is exactly performing Thompson sampling. And so I think the intuition for this is that by us going back and relabeling what was the action that should have been optimal at that point, and then training a supervised learner, what we are doing in that case is we're learning to predict a distribution over what is the optimal action, given the data that has been observed so far. So under the assumption that the learned model is consistent, this is a big assumption, but this says that given enough data, we are able to actually learn this Bayesian probability distribution over the data generation process. And I know I'm not defining all of these terms, but just to give it a high level of sketch. And then the second really important thing is that the way that the data is generated is what we're calling here compliant, which what we mean in this case is that the way that actions are taken only depends on the prior data for that task. So this would be violated, for example, if you have an expert making decisions. If an expert already knows the optimal way to do this task, they could be making decisions at every time point that don't actually just depend on the history. So if you have something like a random algorithm or reinforcement learning algorithm, it will only be using the historical data. So we rely on that assumption here. And then under that, we can show that essentially the posterior distribution that our decision pre-trained transformer is learning is exactly the same as what you'd get with posterior sampling. Okay, now why is that significant? Well, that's significant because basically it's helping us solve this problem without actually having to write down a particular parametric assumption for those priors. We're relying on the transformer to represent whatever is the sort of data distribution task. And we're showing that this will actually mimic Thompson sampling, which means we're going to inherit all the guarantees for Thompson sampling. So in particular, I think this is the, we had a number of different empirical results in the paper, but the one that I like the most is this one, which is, I think this helps tackle the question of what do we do about model misspecification, or can we learn from historical data what are these kind of structural priors without actually writing them down in advance. So in this particular setting, it's a small case. I think it was just 10 different actions. It was a linear bandit case where we had a small number of actions and we wanted to learn, what was the best way to make decisions. But all the arms actually had features, but the algorithm that was being used to gather data ignored those features. So we know that, because we specified the system, that it's actually a linear system, a linear reward system. But the algorithm that's being used to make decisions just was treating it as if like all of those actions were totally independent and their rewards could be completely different. And as you might imagine in that case, so here on the y-axis is regret, so higher is worse. So in this case, like we get quite a lot of regret because the algorithm that's being used doesn't know the structure of the task. And so it's learning to figure out the optimal arms over time, but it's pretty slow. Now, instead, if you actually give the linear structure, you can do a lot better, because now if you give it to an algorithm like linear upper confidence bounds, it has a much smaller regret because it can leverage the fact that it knows the reward structure is linear. But the really nice thing is that our pre-trained, our decision pre-trained transformer also can get that same gain, because it can learn from all of those multiple tasks that given this representation, it can learn an embedding that essentially is saying, this is a linear task, and so then if you give me a new task, I'm going to assume we're still in the same distribution, and so therefore I'm going to treat it as if it's got this linear structure. So, and in particular, it'll guarantee that you have this Bayesian regret, assuming that you're still in the same distribution. So I think that the key gains of this is that it's allowing us to do posterior sampling in sort of a computationally efficient way that allows us to reflect this latent domain structure. I think there's an enormous amount to continue to be done in this case. For most of the complex tasks that we want to think about, we don't know what those structures are, and so being able to do this kind of model selection is really important. The method that I just showed you is, I think, an interesting first step, but it still has lots of limitations. So for example, if you have non-stationarity and your data distribution is changing over time, which I think is very common in many real-world applications, this will not automatically adapt to that. And work from Chelsea Finn on MAML and sort of meta-learning has this nice capability that it will adapt to non-stationarity. So I think there's a lot of interesting different questions here. And I think this is a nice step to start to think about how we can work in complex settings and leverage that structure. So I know there's not a lot of time left, so I just want to really briefly talk about some ideas around using data better. And in particular, now I'm going to move to the reinforcement learning setting, where instead of making single decisions that don't affect the next state or context, we're going to be thinking about decisions where when we make that decision, it actually influences the next state. And so this comes up a lot in the education work I do, where our whole hope is that as we provide exercises to students or videos, that we are actually helping them transition into new states where they know more. And of course, in reinforcement learning, the big challenge is that we don't observe the reward function and we don't observe the dynamics. We just have this through data. So we've done a lot of work on, and a number of other people in the audience has also been thinking about this, is the case where we have access to some historical data set, and we want to leverage this and learn a better decision policy for future use. And I just want to highlight here that so I was rethinking about this recently due to some other work that I've been doing with Stefan Wager and Yu Chen and some other wonderful colleagues, and the difference in the settings there compared to the setting that I'm talking about here, which is the real challenge in this case for us is distribution mismatch and finite behavioral data, finite, historical data. And the key challenge is that sort of different decision policies are going to induce different state and action distributions. And then given a historical data set that's gathered by a particular behavior policy, those, if we want to consider how new policies might work, those new policies might have different effective sample sizes in your historical data. And essentially, this is just like matching. You know, if you have one way that you've been sort of providing recommendations to customers and you want to think about different ways, some of those new ways might overlap more or less with the historical data that you have. And the challenge with that, of course, is that that introduces variance in terms of how precisely you can estimate the performance of different decision policies. So in general, we're really interested in the case where you have fixed data and you can think of all sorts of decision policies and you'd like to use that fixed data to select among those. And the problem is that the accuracy of how well you can estimate those might vary a lot depending on how much those policies overlap with your historical data. So this is something that has been known for a while. There's some lovely work that came out of Cornell on this, counterfactual risk minimization. There's some great work from reinforcement learning, observing this being a big problem in practice for deep RL. So a number of people have been thinking about this in the past. But when we started thinking about this, we wanted to sort of switch what we were aiming for, which is instead of trying to find a near optimal policy, we wanted to sort of find a really good policy that was covered in the data. And what I mean by that is that sort of we had sufficient data support that we thought we could get accurate estimates of its performance. So in this case, sort of the main idea was that we wanted to be pessimistic with respect to our uncertainty over the performance of these policies. And I just want to highlight that, at the time we started doing this work, there was more and more interest, and in general in reinforcement learning, there's been more and more interest in how to leverage historical data to make good decisions. But there were still quite a bit of limitations in these approaches. And I find it really informative often to think about really, really small settings to try to clarify my own understanding about what is the challenges. And so here we have this, we often call these chain worlds or sort of chain Markov decision processes. I won't go into it, but just suffice it to say, this is like a 10-state Markov decision process. This is tiny. But what we are illustrating here is, I think, some concerning behavior where as you vary the amount of historical data you have on the x-axis, the success rate in terms of us being able to learn a good policy from it, and in particular being able to learn the optimal policy, has this sort of concerning U-shape, where as you get a little bit more data, given the stochasticity of the system, your algorithms might actually start to pick the worst policy. And then, of course, asymptotically, as you get really good coverage of data from all possible states and actions, everything does well. So I think what we were really observing in this case is just that, when you have finite amounts of data and you have stochasticity, then you're going to get a lot of error inside of your estimates of the policy. And so we want to think about that when we're trying to learn good policies for future use. So our key idea in this case was very simple. Our idea was just to sort of use a very simple threshold over, do we think we have sufficient density in this, parts of the state and action space, where we think we can be confident in doing estimation over the policy performance in that space. And so in this case, we just used a very simple threshold. We just said if we have sufficient density, we're going to be able to trust our estimates for that state and action, and else we won't. And so then for those of you that are familiar with Bellman backups, essentially we're just modifying some very standard approaches to learning policies for Markov decision processes by including this sort of filter function where we zero it out if we don't think we have enough data support for trying to estimate accurately the performance of the policy in those states and actions. And so essentially this introduces pessimism, which means that the policy we learn is unlikely to visit parts of the state in action where we don't have very good support. Our focus was really in changing the types of theoretical analysis that people were focused on, and instead of making strong assumptions that you did have coverage over any possible policies, states, and actions you'd visit, to move to more of a case where we're just trying to say we're going to learn a policy that is near optimal within the data support. So happy to talk about those theoretical results offline. I think to me, one of the things I want to highlight here just at a high level is that by doing so, you really can get substantial gains in a lot of empirical settings. So this is Hopper, which is one of the Mujoko tasks, which is a standard set of sort of like control and robotics tasks that's been very well studied in the offline reinforcement learning community. What you're seeing here is this is a fixed amount of data, so I'm not changing the amount of data. I'm just changing how many steps that the algorithms are working with. And what you can see here is that the gray line is the performance of the policy in terms of the historical data. So this is sort of like actually how good was the policy that you gathered data from. And what I want to highlight here is that if you have sufficient variability in your historical data, you can leverage that to figure out a much, much better decision policy. And that green is ours in this case, and it significantly outperforms some of the other approaches that people were doing. I just want to mention in this case that I think pessimism must have been in the water in 2020 for many reasons. And so in this case, many people started thinking about pessimism. And so there was a number, I think there was maybe 4 papers at NeurIMS this year that all had very related ideas. Including some from people in this audience. So I just want to highlight that there's a lot of different ways you can put in pessimism under uncertainty. We did some benchmark comparisons to a few different domains, and we saw that, as you might expect, some of the times our method works a little bit better, sometimes their methods work a little bit better. But I think these ideas have continued to influence the community, and in particular CQL, for example, which takes a different sort of form of pessimism and conservatism, has ended up being very widely used. So just to highlight here, I think that this is sort of an instance of how do we better leverage historical data and think explicitly about our uncertainty over our ability to estimate the performance of different decision policies. I think there's still an enormous amount to be done in this space. In particular, compared to a lot of supervised learning, we just don't have very good off-the-shelf tools and packages where a random person who's a practitioner can just take these methods and have them reliably work. And so that's something that we've been working on, and I think a lot of other people are working on as well. So just to highlight today, I've really talked mostly about these first 2 thrusts. These are, and given some illustrations of the work we're doing there. I do want to highlight this third thing that I didn't talk about today, which is really, I think most of the incredible successes we've seen in machine learning over the last decade have been due to a particular formula, which is you combine large amounts of data and large amounts of compute and really powerful function approximators, aka deep neural networks. And that's been used, of course, both for things like large language models, but it's also been used for things like AlphaTensor and AlphaGo, and their recent results using reinforcement learning to get a silver-level math Olympiad. But in all of those cases, one either had access to huge amounts of historical data or simulators of a system that allowed one to essentially generate huge amounts of data. And one thing that I've really struggled with often is sort of when we think about things like healthcare and education, we don't have really good simulators, and we have much less amounts of data than we do on the internet. And so one thing that we've been thinking about recently is how can we use things like large language models to synthesize data, say about students or about teachers or educational experts, so that we can start to apply that very successful formula to a lot of other domains that are more focused on sort of directly supporting people and their goals. And so with that, I'll just close and say I think there's an enormous amount still to be done. And I think as we make progress on these, we can really support all these applications that could enable human flourishing. Thank you. Yeah, great question. So you're asking me about that I make the assumption in the decision-pretrained transformer that we have access to the optimal actions, or we could learn them and relabel, and when is that realistic, and if that fails, how well do we do? I think that it varies. I think that often, we can get a pretty good approximation if we have sufficient amounts of data. I think in things probably like online commerce and others, it's not a bad approximation. There have been, you can, of course, this is what allows us to show that it's the same as posterior sampling. You can certainly run it with any actions that you label it with. We just won't have theoretical guarantees. We haven't done this, but some other people have recently been starting to do work on the case to think about if some of those actions are suboptimal and how does the performance go. So I think it's an interesting area for future work.
Question about the data synthesization and bias, particularly in an educational context. When you're doing the reinforcement learning and aggregating that data, how would you sort of manage that? I'm from the Philadelphia area, I'm in education, and I see the bifurcation in learning outcomes, and there's a lot of concern, particularly for my demographic, about it, trying to African American. What can we do in your space to mitigate?
Yeah, I think that's a great question. So for those who didn't hear it, the question was around thinking about bias and the potential of these algorithms to perhaps even further amplify inequities and amplify bias. I didn't show this. One of my favorite recent results is where we have a new educational system where we then examine who it was helpful for, because I have a big concern that some of these are just going to make the rich get richer. And we found there that it was particularly helpful for the lowest performing students, which I found really exciting. One thing that we do try to increasingly do is a lot of these ones sort of focus on expected outcomes, but we're trying to do a lot more analysis of subgroup analysis to understand who is it helping and how much is it helping them or not, so at least we can be much more aware, and then ideally put that into our objective function so we can make sure that we actually are supporting all the different groups we want to. It's a great question. Thank you. Yeah, that's a great question. So the question was saying, like, the motivating example for some of this work was thinking about a charity where they could not update the software in real time. So in that particular case, we have not used this for there. We ended up focusing on a different first thing, which was diagnosing why students were struggling. So this is more a case of sort of theory and algorithms being inspired by that, but not yet closing that loop. We have used these ideas, as I was just saying, for some other cases where we have those educational interfaces in-house. And in those cases, we've used these types of procedures and offline learning to learn policies that we then have tried and seen how effective they are in practice.